Today I will be talking about Phytonet, a phytoplankton-powered biobatteries for regenerative low-powered internet infrastructure. So to set the context, the demand for the digital service is growing at an unprecedented rate, like cloud computing, artificial intelligence, and billions of IoT devices are transforming how we live and work. But they are also requiring a vast amount of energy. So globally, the ICT sector is now responsible for around 4% of electricity use and between 2 to 4% of greenhouse gases emissions. According to a study by Jones in 2018, the energy demand by communication technology will accelerate in the 2020s, and that the network infrastructure and data centers will take a large slide. So today the demand is already straining our local power grids. For example, recently Microsoft and Amazon need to abandon plans to build new data centers in Ireland because the national power supply cannot meet the additional load. And as MIT's electrical engineering professor Vivian C. has observed, efficiency alone cannot solve the problem. Because once things become efficient, we just use more of them and trash them, which increase our overall carbon footprint. This means that mitigation strategies are not enough. We need to explore regenerative approaches, designing digital infrastructure that not only consume less, but actively contributes back to the ecological systems. So in nature, nothing is wasted. For example, the forests recycle nutrients, wetlands cleans water, and also providing food. What if our digital infrastructures work the same way? Not just with doing less harmful, but actively regenerative. So imagine web servers and sensors that don't just consume electricity, but also clean water, capture carbon, or even provide habitats for wildlife. Or imagine electronics that sleep and wake in the rhythm with the sun, just like living organisms. In other words, instead of building extractive system, we can start designing symbiotic system where digital network functions like ecosystem, which is local, adaptive, and multifunctional. So this is where Phytonet comes in. The idea of Phytonet is a floating web server powered by phytoplankton through biophotovoltaic system. It integrates energy harvesting from phytoplanktons in waterways, carbon capture through photosynthesis, and IoT hardware for sensing and data sharing. Here's how it works. So the microalgae will grow on the electrode, forming biofilms, and as they photosynthesize, they absorb carbon dioxide and release oxygen. In this process, they also produce electrons. So when connecting these two electrodes together, it creates a flow of electrons, and it can power external load. Well, the power output is not a lot, it's like milliwatts, but it's enough to run microcontrollers and environmental sensors. And those sensors can monitor water quality and share the data on a web page. So this is both an energy system and a prototype for a regenerative digital internet network. So our approach combines science and design. We use speculative artifacts to explore public imaginations, sampling canal phytoplankton samples to grow biofilms on electrode materials, and fabricate two biophotovoltaic prototypes. And at the end, we also measure the electrochemical performance of these cells. We create a speculative artifacts like prompt cards and mock news articles to get people thinking, what if the internet can run on algae? Participants combine scenarios from smart canals to community-run clean water networks. So we also these are some of the news articles that generate from the scenario building, covering from the legislation and some socio-economic aspect. We also interview stakeholders to highlight the needs of independence from corporate control service, and also how the algae-powered servers can help cleaning water. So on the technical side, we collect phytoplankton from London's Regent's Canal. We enrich it and inoculate on different electrode materials. Like we test on platinum wire, stainless steel mesh, graphite, and aluminium wool. The best performance was aluminium wool because of its porous surface, allowed algae to attach and grow strongly, forming a living electrode. So we built 2 BPV prototypes, an open flat plate design with aluminium wool as the anode and a platinum-coated carbon paper cathode. In this design, we connecting 2 BPV units in parallel. And in the second design is a floating tubular biocathode with using the same aluminium wool as anode, but then using a biocathode with plant root and carbon fiber. We conduct the BPV units we conduct the electrochemical testing by connecting the BPV units to external variable resistor. So the voltage was measured and the current was calculated. This gives us the polarization curve and the power output data. For the flat plate design, the peak power output reached 3.4 milliwatts per modules, and the current density reached 896.8 milliamps per square meters. While the tubular design performed less well in terms of power density and current density, but it offered better buoyancy and integration potentials. So from the top graph, it shows the open circuit voltage time graph. It shows that both BPV systems can run in a stable operation for over 30 days, following the patterns of the daylight pattern cycles. And then this is also, you can see there are the biofilms growth on the aluminium anode on both design and how it performs on in the field. So because the BPV power output is relatively small, so we explore different ways to connect the units to increase output. For example, in series to increase the voltage, or in both parallel and in series to increase both current and stability. With the 4 units connect in parallel and series, we could anticipate generating 13.6 milliwatts and 13 milliamps, enough to power a sensor node with the integration of power management systems, with energy storage and the deep sleep cycle. So here is the proposed IoT network architecture. Each node will include a BPV stack, energy harvesting systems, microcontroller, and local storage units, and a transmitter. So here, these nodes will be operating on duty cycles, spending most of the time in deep sleep, and briefly wake up to measure and transmit data. And these nodes are connected locally in a mesh network, and data is shared via a lower WAN to the internet. This makes the network ultra low power and decentralized. Based on our findings, we suggest the Phytonet can be potentially applied in powering small devices like the low-power thermometers and humidity sensors. And it can be also function as a biosensor, because since the microalgae or the phytoplankton, their photosynthetic activities will change with water quality. We also envision it can be embedded in the Internet of Biological Things, serve as the living energy harvesting node, powering a biohybrid sensor, and could monitor environmental conditions, self-sustain without external energy, and communicate through lightweight wireless links. So Phytonet is a proof of concept. So next step, we need to conduct more like community deployments. For example, developing DIY kits for citizen scientists to test the BPV unit in local waterways. and long-term study to see how floating BPVs will interact with wildlife and the ecosystems. So to conclude, the internet is one of the fastest growing energy consumers on the planet, but with projects like Phytonet, we can reimagine infrastructure that is regenerative, local, and ecological, not just consuming energy, but also giving back to the system it depends on. And here I will also, at the end, also thanks Dr. Lorraine Archer for guiding, for supervising this project during my study in the Central St. Martins. Thank you.
Thank you very much for the nice presentation. We are almost a little bit out of schedule.
Yeah.
So I would kindly request if there is any question, just to be able, there is work performed on this issue on the Q&A panel, and I'm almost sure that Maria will be available to answer whatever is needed. Thank you very much once again,
sure.
Maria.
Thank
And
you.